We're going to spend some time over the next couple of days looking into vectors in a little more detail. So the first concept that we're going to think about is the vector magnitude. Now remember, we said that vectors are quantities that have both a magnitude and a direction. So what we'd like to do is, using the notation that we've found so far, figure out how we can find the magnitude of a vector, that is, its length. So the magnitude or length of a vector is the length of any of its representations. It doesn't matter where we start it. And we'll usually denote it as follows, with it looks like an absolute value, but here it's meaning find the size of vector v. And occasionally in some textbooks you'll see that they use double straight lines, but we'll mostly be using single straight lines. And the length of a two-dimensional vector should look vaguely familiar. So if we have a vector A that has components a1 in the x direction and a2 in the y direction, then the length of that vector is the root of a1 squared plus a2 squared. And if you take a moment to sketch a vector in 2 dimensions, then what we have is that its x dimension is length a1 and its y dimension is a2, and so by Pythagoras we know that a1 squared plus a2 squared is going to give us the length of the vector, which is what we want. So that's going to give us the length of the vector squared. So this is Pythagoras. And in order to get this formula up here, we've just taken the square root both sides. And in exactly analogous way, we can find the length of a three-dimensional vector by summing up the squares of each of the three components, so the x, y, and z components, and then taking the root. And that gives us the length of a three-dimensional vector. Now we have three special vectors that play an important role when we're in R3. So this is when we're in 3 dimensions with an x, y, and z coordinate axes. And these three vectors are written as follows. So the first one is called I hat, and this little sign on top of the I, which looks like a little cuppy, says that this vector, this basis vector, has length 1. So our little hat means has length 1. So our I hat vector says move 1 in the x direction and don't move at all in the y or z direction. Then we have the j hat vector, which moves us 1 unit in the y direction, and we have the k hat vector, which moves us 1 unit in the z direction. So I hat is related to x, j hat is related to y, and k hat is related to z. And these are called the standard basis vectors. So the idea we have is, if we draw our coordinate system in 3 dimensions, then our I hat vector, which is this one over here, points 1 unit in the x direction, so that's our I hat, and our j hat points 1 unit in the y direction, and finally our k hat points 1 unit in the z direction. So we should have a hat on top of j, and we should have a z up here. And what we're going to do is use these three vectors to express any vector given in component form, with components in each of the 3 directions. So let's look at an example of that. So we have the vector 1, minus 2, and 6. So if you remember what this says go 1 unit in the x direction, 2 units in the minus y direction, or you could say minus 2 units in the y direction, and then 6 units in the z direction. And we can write this using our basis vectors as, well, go 1 unit in the I hat direction, so go I hat, and then we want to go minus 2 units in the y direction, so we're going to subtract from our I hat minus 2 times our j hat, and then we want to go 6 units in the k direction, in the z direction, so we take 6 times our k hat vector. So we've gone from writing things in component form like so, to over here writing as a sum of vectors going in different directions, but it comes to exactly the same thing. So let's see how we can use addition and subtraction to when we've got things expressed as basis vectors. So here we have a vector A, which consists of components go 1 direction, go 1 unit in the x direction, 2 units in the y direction, and minus 3 units in the z. And our B vector says go 4 units in the x direction and 7 units in the z direction, and we're not moving in the y. And what we'd like to do is express the vector 2a plus 3b in terms of I, j, and k. Well, let's take this step by step. So we want to do 2a plus 3b. So we want 2 times, now a is given by this expression over here. So that's I hat plus 2j hat minus 3k hat. Plus, and then we've got 3 times b, which is 4i plus 7k. And now if we multiply in by this 2, we're going to get 2 units in the x direction, 4 units in the y direction, minus 6 units in the z direction, and we want to add 12 units in the x direction and 21 units in the z direction. And now we're going to group like terms because we've got 2 units in the x direction plus another 12, so that's going to give us 14 units in the I direction plus, well, we've got this 4 in the y direction and no others, so that's 4 in the y direction, and then we've got minus 6 plus 21 in the z direction, which gives us plus 15 in the z direction. So all we're really doing is creating a different way of expressing vectors, and it turns out to be useful to be able to think of vectors as being composed of scalar multiples of each of the basis vectors. So we've already actually seen 3 unit vectors. Our basis vectors are unit vectors because they have length 1. But it might be useful on occasion to be able to take any old vector, not one of our basis ones, and find the unit vector in the same direction as that vector. So let's just clarify what we're doing. A unit vector is a vector with length 1. If we're not dealing with the 0 vector, then the way that we find the unit vector in the same direction as any old vector is we take our vector of whatever length and we divide through by its length. So let's see how this works. We want to find the unit vector in the direction 2 in the x, minus 1 in the y, and minus 2 in the z. Okay, well, we're going to call this our vector A. So we know that the unit vector A is going to be equal to our original vector divided by the length of our original vector. So what we need to do is we need to find this length over here. Now remember, when we write a vector in this notation over here, it is just the same as simply writing down the components. So we could have written this as 2 minus 1 minus 2. And we know that our length of a vector is the square root of the sum of the squares of the components. So that'll be 2 squared plus minus 1 all squared plus minus 2 all squared, which gives us the root of 9, which is just 3. So our unit vector, so this is the vector of length 1 in the same direction as vector A, is equal to our original vector A, which is 2i hat minus j hat minus 2k hat, divided by 3. So if we want to have this looking a bit more normal, we'd have 2/3 I hat minus 1/3 j hat minus 2/3 k hat. And my claim is that the length of our vector A hat is equal to 1. So we're hoping that because we've done this crazy thing, dividing the original vector by its length, that we've now ended up with a unit vector which has length 1. Well, let's just quickly check. We know that the length of any vector is the root of the sum of the squares of the components. So we've got 2/3 all squared plus minus 1/3 all squared plus minus 2/3 all squared. And if you do this multiplication, you'll see, well, we've got 4/9 plus 1/9 plus 4/9. We're going to take the root, and this is the square root of 1, which is just 1. Because remember, we've defined this as the positive root. Okay, so now we know, if we're given any old vector, how to find a vector that points in the same direction but has length exactly 1. So that's unit vectors. So we've talked about adding and subtracting vectors, we've talked about scaling them by a scalar and finding their length, and the next thing we need to do is think about multiplying vectors. Now it turns out that there are two different ways of multiplying vectors. The first way, which we're going to look at, is called the dot product, and this gives, as a result, a scalar. When we look at the cross product, this is a way of multiplying vectors that gives us a vector as a solution, but we'll come to that in the next lecture. For this lecture, we're going to look at the dot product. So our dot product is also sometimes called the scalar product because the result gives us a scalar. Remember, a scalar is a single number. So how is this dot product defined? Well, it's only defined for non-zero vectors, and it is defined, so our a dot b, so we would read this as a dot b, is equal to the length of a times the length of b times the cosine of the angle between them, where the angle between them lies between 0 and pi. So if you think about it, remember that we have 2 pi radians in a full rotation, so we always take the smaller angle between the vectors when they're drawn from the same initial point. So for example, if we have these two vectors, we will take the smaller angle, theta. And just so that we have the definition for everything we need, if either of our vectors is actually the 0 vector, we're just defining straight away that their dot product is 0. So what is this dot product useful for? Well, it gives us a way of seeing how much A and B point in the same direction. So if, for example, we have an A and a B that are pointing quite a lot in the same direction, then we're going to expect that A dot B is quite big. And we'll see what that means in a moment. On the other hand, if we have our A and our B pointing in virtually at right angles to each other, we would expect that A dot B is close to 0. And anywhere in between, we would expect something in between. So we need to quantify what we mean by big. So let's look at some examples. So to keep it simple, we're going to think about our vectors just in terms of knowing the length of A and B, and we're going to be told the angle between them. We're going to come back to calculating the angle between them, but for the moment we're assuming that we're given that. Okay, so we have a vector A and a vector of length 4 and a vector B of length 6, and we want to find the dot product if the angle between them is 0. So if you think about this case, we're thinking about a vector A, which has length 4, and a vector B. Since the angle between them is 0, they're lying parallel to each other, and something like so. So we expect that our dot product should give a biggish value. Well, let's see. We know that A dotted with B is the length of A times the length of B times the cosine of the angle between them, which in this case is 0. So this is going to give us 4 times 6 times, well, the cosine of 0 is 1. So this gives us 24. And you'll notice that 24 is the biggest possible value we could have for A dot B, because A and B are fixed, I mean the size of A and the size of B are fixed, and changing the angle is going to give us something that lies between -1 and 1, because our cosine lies between -1 and 1. So when cosine is equal to 1, we have the biggest possible value for our dot product. So let's see what happens when we take the angle pi over 3. So pi over 3 is roughly 60 degrees. So we've got something like this. So we've got a B and an A. And that's pi over 3. And now let's have a look. A dot B is going to be equal to 4 times 6 times cos of pi over 3. And if you check, cos of pi over 3 is a half, so this is going to give us 12. So this is saying, if we think about our vectors A and B, then A is going some of the direction, in some of the direction of B, but it's also pointing away from B somewhat. So notice we've got 12, which is quite a lot smaller than 24. Okay, if we now look at angle between being pi over 2, then what we've got is our A is pointing up like that, and our B is pointing at right angles. And in this case, we can see A is not pointing in the direction of B at all. So we would hope that our dot product is 0. Let's just check. It's going to be 4 times 6 times cos of pi over 2. And if you check, cos of pi over 2 is 0, so we get 0. Now let's have a look at what's happening when we've got the angle between them is 2 pi over 3. Well, then we've got our A is pointing in that direction, our B is pointing in that direction, and this angle here is 2 pi over 3. So now we have A is pointing somewhat away from B and also somewhat in the opposite direction of B. Let's see how the dot product changes. So we've again got 4 times 6, and we've got the cosine of 2 pi over 3. And if you plug that into your calculator, you'll find that that's minus a half, and so we get minus 12. So if we compare these two, our angle being pi over 3 and 2 pi over 3, in our first one, A is pointing somewhat in the same direction as B, but in the 2 pi over 3, it's pointing in the opposite direction to some degree, and that's why we've got this minus sign over here. Alright, let's have a look and see if our angle between them is pi. Well, that means that A is pointing in one direction and B is pointing in the opposite direction. So if we think about how it compares to our first case over here, here we got positive 24, which says A lies in exactly the same direction as B. Now we've got A lying in exactly opposite direction. So we should get minus 24. Let's just check. Now the cosine of pi, if you check that, is equal to minus 1, so we end up with minus 24. And if you want to check our final thing, where our angle between them is 5/3 pi, then we've got say B pointing in this direction and A maybe pointing down like this. Well, if this is 5 pi over 3, then we actually use the smaller angle, remember from our definition. So we're going to have a full revolution is 2 pi minus 5 pi over 3 is going to give us 1 pi. Sorry. It's going to give us pi over 3. And so that's going to give us 12 again. Okay, so we've seen that the dot product gives us a way of measuring how much two vectors point in the same direction. One thing that's important and is very useful is to note that if two vectors, A and B, are at right angles to each other, that's the only time that the dot product is 0. So this gives us a way of checking if we're given two vectors. We can check very quickly if they're orthogonal or not. Compute the dot product. If you get 0, you know they're at right angles. If you don't get 0, then they're not at right angles. So you might be wondering, if our vectors are in components, then how do we calculate the dot product? And what we have over here is the requisite formula for vectors in components. So we're going to jump straight into the three-dimensional version. So if we have a vector A with components A1, A2, A3, and a vector B with B1, B2, B3, then A dot B is given by, you multiply the first components of each vector and add it to the second two components multiplied, added to the third two components multiplied. So this is very quick, no worrying about causes and things like that. So here we go. If we look at an example, so we've got a vector in component form, which is -1, 7, 4, and the second vector is 6, 2, -1. Well, if we want to take the dot product, so it's important that you keep the dot if you've got a dot product, then we're going to have -1 times 6. That's our first components multiplied together, and we're going to add this to our second components multiplied together, so there comes our 7 dotted with 2, And then finally our third component, so it's going to be a 4 dotted with minus 1. So we've got minus 6 plus 14 minus 4, so in total that gives us 4. And we can do exactly the same thing if we have our vector expressed in Ijk notation. So I shouldn't have had square brackets, they should be round brackets. Well, again, we can just look at this and we can say, I'm going to take the coefficient of the I component in our first vector and multiply it by the I component in the second vector, which is 0. So actually, let's just write these out properly. I've got I hat plus 2j hat minus 3k hat dotted with, now I have 0 I hat plus 2j hat minus k hat, and off we go. I'm going to take this 1 times 0 plus 2 times 2 plus minus 3 times minus 1. So this term is 0, this term is 4, and this term is 3, so we get a total of 7. So we've really looked at three different expressions for vectors and how to calculate the dot product. And these, which one you use, will depend on the particular scenario that you're working on. So there are some properties of the dot product that are useful. For example, it shouldn't come as a surprise if you dot a vector with itself, then you get the length of that vector squared. This makes sense because a dot a is going to be equal to the length of a times the length of a plus the cosine of the angle between these two. But if you've got the same vector, it's lying, each vector lies on top of each other, so our angle is 0 and our cosine of 0 is 1. So that's how we get that if you dot a vector with itself, you get the magnitude of the vector all squared. So the second thing to notice is it doesn't matter what order you do your dot product. Whether you say a dot b or b dot a, you're going to get exactly the same answer. So this says that our dot product is commutative. We're making a bit of a big deal out of this because when we look at the second kind of multiplication, it's going to turn out that that one is not commutative. So dot product is, but the cross product that we're going to learn about is not commutative. The other thing that's useful about the dot product is it kind of acts like multiplication in real numbers acts with addition in real numbers. So if we're taking a dotted with some sum of vectors, it's the same as saying a dotted with the first vector plus a dotted with the second one. So dot product distributes over vector addition. And similarly, if you're scaling some vector and then dotting it with another vector, you can also just take the scalar out, do your dot product first, and then scale. Or in fact, you could scale the second one by the same amount and then do your dot product. And finally, if you take the 0 vector and you dot it with any vector, then you end up with 0. So spend a little time getting familiar with dot products, and once you have done that, you can move on to this next section which uses the dot product. So we've now got the idea of projections. We've got two vectors, a and b, which can be pointing in any direction, but they have the same starting point. And in this case, it can be useful to split our vector b into two components, one that's parallel to a and one that's orthogonal to a. So what is it that we're doing? So we've got, say, for example, a vector a and a vector b. And we're going to write our vector b as a sum of two vectors, one vector which goes parallel to A, so we're going to call that B parallel, and we're going to add to B parallel a vector B perpendicular. So we've got B parallel moves in the direction of A, and then B perpendicular moves perpendicular to A, and that gives us, if we add those two together, our original vector B. So we're expressing our vector B in terms of things parallel and perpendicular to A. So how can we do this? So the scalar projection of B onto A gives the length of the component of B parallel to A. So in our previous drawing, what we called this thing was B parallel. And in order to find this, we take the dot product of A and B, and we know that that gives us a measure of how much A and B point in the same direction. And then in order to get the right sizing, we divide through by the size of A. One way to see how this works is, let's remind ourselves that A dot B is really the length of A times the length of B times the cosine of the angle between them, and we're dividing through by the size of A. So since we can cancel our length of A top and bottom, what we really end up with is the length of B times the cosine of the angle between them. So that is projecting our vector B, or rather it's projecting our vector A onto our vector B. So what we've got, if these are our two vectors, there's our B, there's our A, what we've just found is the length of B cos theta. And if you think about that in terms of the trig that you know that B is the hypotenuse in this case, and our cosine of theta is adjacent, which is this bunny over here, divided by that length there. So that's how we get that this component over here is the length of B times cosine of theta. So that's just giving us the length of the projection of B onto A. But if we want to get the actual vector, then what we need to do is multiply our, so what we need to do is we need to multiply our B cos theta by a unit vector in the direction of A. Another way of thinking about this is if our definition is given as follows, what we've got over here is, so A dot B so I'm splitting up this into two lengths of A. So we know that this thing gives us the length of the component of B that is parallel to A. And then we have as a remainder here our vector A and the second of these two lengths of A's. And this over here is the unit vector in the direction of A. So let's have an example. So we're going to find the scalar and vector projections of our vector B, which is going to be 1, 1, onto our vector A, which is equal to minus 2, 3. So we're going to just do the calculations and then see if we can draw a diagram that's going to help. So we know that the component of B in the direction of A is given by A dot B over the length of A. And if you check that, our A dot B is going to be minus 2 plus 3, which is going to be 1. And if we have a look, our length of A is going to be the square root of 2 squared plus 3 squared. So that's 4 plus 9, and the root of that. So we've got the root of 13. And our projection of B onto A is going to be 1 over root 13 times by the unit vector in the direction of A. So let's do a sketch here. We'll try and do this as accurately as possible. So I'm going to have my y-axis and my x-axis. So let's have 1, 2, 0, minus 1, minus 2, and 1, 2, 3 in my y direction. And let's plot out two vectors. So our vector A is minus 2, 3. So we go minus 2 in the x direction and 3 in the y. So if we start from the origin, our vector A looks like that. And our vector B looks like 1, 1. So our vector B, starting from the same point, looks like so. So what have we found when we found the projection of B onto A? Well, this says we want a unit vector in the direction of A. So a unit vector times by 1 over root 13. So we've got some, so a unit vector would be roughly this length, but 1 over 13 is going to give us roughly this length. So this itty bitty little thing over here is our 1 over root 13 in the direction of A. And if we were to extend this a little bit more, you'd notice that if you were to draw a line perpendicular to the little component that we just found, that would give you another component for B, so that we can in fact write B as this component, which is in the direction of A, plus this component, which is perpendicular to A. So for homework, you can find the scalar and vector projections of these two vectors. So we're wanting B onto A, and notice that they are three-dimensional, but you use exactly the same technique. So give that a try and then come back and check the notes.